Okay folks, as you can see my name is Gary Bulmer and my background is software engineering and computer science. So I learned to use Unix machines in 1983 when I learned my C, and I've been writing software and managing software groups and software products since then. I got interested in education a few years ago, and so I've been going out and using Arduinos to try and get kids interested in making things instead of watching telly, basically. And so my talk is about the question of what happens after Arduino, and I've been trying to come up with an answer. Is it the best answer? Probably not, but it's an answer. That's what I'm basically going to describe. So, I assume that there's some knowledge of what Arduino is. Skip over that. What's the problems with it a little bit, and what have I been doing, and then a kind of an appeal if anyone in the room is interested. Would you like to help me? So Arduino, that's one of these little microcontrollers, and so it basically plugs in over a USB cable. You run your compiler on your host PC, which could be Linux, Mac or Windows, and the actual program runs on the chip, and it's got, and this is a fairly modern one, and so this has 32k bytes of program memory and 2k bytes of RAM. So this is a big one, plus people started out on much smaller systems. But the important point is, it's real time, there's no operating system, there is zero between the library and the hardware. It runs at about 16 megahertz, which is far faster than even you guys can think. And so little things it can do very, very quickly. And it is just about possible to create a television picture by wiggling its pins. That's about how fast it is. And they're insanely popular because it was designed to be open source, and it was designed to be used by people who didn't really want to become experts in using microcontrollers. It was designed for people who needed them as glue in order to make a project. So it was designed for artists and designers and people who've never really been interested in this stuff. And so you don't need a manual in order to make use of it, because most of the instructions are printed on the board. The software is open source. If you hand this to a child above about 7, they know how to wire it up because it's just a USB cable. And if you don't tell them that they're writing C++ programs, they just get on and do it. Okay? That's the beauty of it. So under the covers, it just uses GCC and a very, very, very tastefully done library. Unbelievably subtle, because people don't even think about it. So I've been using this with school children of 13 to 16, and then adults from 18 to over 80, I think, in various contexts. So I've been going into schools as a science, technology, engineering and maths ambassador, and running little workshops where we try and build a robot in a day or an hour a week over 5 or 6 weeks using this. And the goal, of course, really is just to get children to be confident that they can make stuff instead of having to assume that is impossible. I deeply believe that unless you try to make things, you don't necessarily learn certain skills. And so, interestingly, when we try and make robots, you discover that quite a lot of children, 14, 15, have never picked a screwdriver up in their entire lives. They've never tried to cut a piece of wire with wire cutters. And these are things which, if you learn them while you're not thinking about them, it's very easy. If it becomes an issue, people, especially the young, resist like crazy because it seems to be a point of embarrassment or inferiority. So really, at one level, it's just an environment in which they can try things out. A few of them get completely obsessed by this stuff, as have I. And so I asked myself, what's wrong with this? And there's very little wrong with it when you start, but after a while it becomes frustrating because you want to make your own electronics. You want to have much more complex systems. Now I'm interested in micromouse and robotics, and I'm also interested in making music and having sound synthesizers. This is not quite up to it. So that's kind of the background. So it's a fabulous piece of hardware, undoubtedly. it has unleashed an enormous number of people in this world. So it's based on a little microcontroller, the chip. It's got a USB interface, this bit up here. It's got an open source IDE and some extremely well done libraries, and under the covers is GCC, and all of the software and libraries are open source, and all of the PCB CAD is open source. The only thing that is protected in any way is the word Arduino, which is trademarked. But you can pretty much stick Duino on the back end of anything, and pretty much everyone in the world will guess, if they're familiar with Arduino, what this is about. So, what comes after it? Well, this is some of my interests. If you sit down and try and analyse a world-class Micromouse robot, and this is a picture of a world-class Micromouse robot. So, for example, you're maze solving or something. So these are quite small, literally fit in the palm of your hand. You need a little bit more I/O than an ordinary Arduino, and you end up putting little bits of logic in. If you want to do sound, or more precisely you want to do music, the input system, the analog input system on an Arduino is a bit slow. You're probably familiar with the kind of Nyquist limit theory, which is 2.1 times the frequency is the number of samples in order to reconstitute, and in practical reality that's rubbish, because in practical reality you want somewhere between 4 and 10x the highest frequency, so you can reconstitute it properly. So really what you want is something for music which is, order of magnitudes several times higher than an Arduino. And what you'd really like, just to be able to play around with this, is digital to analog conversion 2, so that you can just play around with making musical things, if you want. And that interests me a lot. And the numbers I've got out of Atmel, they reckon if you were going to do an MP3 player, for example, not suggesting that's the be-all and end-all, you want about 30 nips. If you're going to do simple vision, you want quite a lot of computer power. So those Arduinos are a little bit underpowered. So my first stab was this thing, which I worked on with a guy called Chris Evans at BCU. And the idea was to make a robot controller, so all you have to do is make a chassis. So down the middle is a microcontroller, stuck on this side are some LEDs, because you have to have traffic light LEDs. Pretty much everybody gets that as a little task at school, and it's really nice for it not to be simulated, but actual LEDs. You can plug servos in, and it can drive a couple of little DC motors directly. And so, just to put it in context, that's this thing. Okay. We built 3, and they work. Get on to how it works in a second, but it's an open source tool chain using GCC with an IDE and libraries and a USB upload. So it's kind of that, but it's a 32-bit system. After talking to a whole bunch of people, most people said, well, the sensor protection mechanism that you put in for children, we don't want it. We'll just get rid of that bit. And then people said, well, I might want to put really big motors on, like I might want to drive a wheelchair. If I want to make a Dalek, people often take a electric wheelchair and mod them. And so I have now moved on to trying to make something a bit smaller, which is this guy. And also, I thought it would be really good fun to try and make it DIY-able. So, what's more satisfying than to get a bag of bits and make a computer yourself? I'm not suggesting most people will ever want to do that. But I think it's very important that psychologically you can always say, well, he's pretty good, but it's not quite what I want. I'd like to be able to just make it myself. And so we've got pretty good at doing surface mount soldering in a little toaster oven. They cost about £15 from Netto and about £29 from Amazon.co.uk. You put solder paste on, like micro miniature icing, dop the parts on, stick it in the oven, and you get reflow soldering, exactly the same, but much cruder, technique that you would use in order to make a mobile phone or a DVD player or a computer. So we've got this not perfected, but this is pretty close now, been around the block quite a few times. And so just to tell you what this thing is in comparison, just to give you a physical comparison between, that's the size of an Arduino, and one of the problems with this guy is it's not on a 0.1 pitch. 0.1 inch pitch is wonderful. There's lots of electronic mechanisms around which, if you can get onto a nice regular 0.1 inch, tenth of an inch pitch, electronics plugs together beautifully. This guy isn't on that pitch, which is mind-bogglingly irritating if you're a kid, because the only way to make nice electronics then turns into a PCB. If it is on 0.1 inch pitch, you can plug it into a breadboard, or you can use a stuff called Veriboard, which is dead cheap. You can get from Maplin's, you know, for most people, half an hour away. So this thing is actually completely on 0.1 inch pitch, and it's got about twice as many IOs as this thing. So this has got about 40 and this has got about 20. And just to go for a more detailed look at it, an Arduino is an 8-bit chip. So those of you who are old enough to remember, you know, BBC Micros and things, they were 8-bit chips, but this thing is tons faster because it's a 16 megahertz RISC. So to put it in context, it's order of magnitude 8 to 16 times faster than a ZX Spectrum, if you're that old. As I say, 32K of RAM, flash memory, and so you program the guy and it holds that program forever. Or, you know, typical estimates are 30 odd years. So every time you put power in, the program fires up and it runs whatever you put in. Over here, the thing that I'm using is a Cortex M3, which is an ARM-designed processor. And the particular flavour comes from ST Micro. I'm using a 64-pin part, which is how I get the extra 20-odd I/O pins on the thing. It runs about 72 megahertz, so about 4.5 times faster. It's 32 bits instead of 8 bits, which often doesn't matter because all you're doing is tootling up strings and characters. But in reality, a lot of the time you're using 16-bit numbers, so it does maths quite quick. And we have a fixed point library for the thing, and so there's a pretty good chance that we'll get Ogg Vorbis across, and somebody's already brought an MP3 player across. And there's a faster part if this one isn't fast enough, which has been compatible, so I'm not going to panic if it's not quite fast enough for all of my mad dreams, because I'll solder a different one in. To put it in context, the part on here, if you bought them one-off from a local electronics store like RS, would be about £3, and this guy, which is about 128k of memory, about 4 times more memory, is about £5. So part cost for part cost is actually comparable, and they're really nice things. So for example, the analog to digital conversion is almost 2 orders of magnitude, about 2 orders of magnitude faster, and that's 10-bit and that's 12-bit. And so if you go and look at theory about sampling systems, you can oversample, and in order to reconstitute or generate, if you inject a little bit of noise, an even higher quality signal. So in theory, you could recover a 16-bit audio signal with that. Plus the highest spec chips have 3 analog to digital converters, so you could actually listen to multiple sound sources. And it's got DMA on board, so it can squirrel all of this away and do things. The highest spec chips have got stereo digital to analog. Again, just 12-bit, but by the time you stick them through crappy earbuds and an MP3, it's probably, we don't know, but we don't think it's very far behind just an ordinary cheap MP3 player. PWM is a mechanism for pseudo-creating an analog output. It's very good for driving motors or servos or timers and all sorts of things. An Arduino has got 6 PWM outputs. The low end, or the mid-end part that I use has 15, and the top end has about 20. So you could actually have about 20 speed-controlled motors driven off the same thing, which is pretty good. One of the things that's very important to us robotic types is we like to try and get feedback from the wheels so that we know how far they've gone. And in order to do that, you normally have a thing called a quadrature signal. It's 2 square waves that just get wiggled if you just imagine you've got stripes on a disc going past a couple of sensors. By measuring the time that the stripe takes to go past the sensor, you can measure velocity. And by just counting them, you can estimate distance. There's hardware inside this chip in order to keep track of that for you. So you can unburden all of that. And the goal here is to allow a 13-year-old child up to a 150-year-old person, if we get one while I'm still alive, to easily build robots and then start ripping off the covers of the software and make it cleverer and cleverer. And you know, if they want it to play God Save the Queen in very high quality stereo at the same time, they should be able to do it. I don't mind. But basically, this is about the right order of magnitude to be an improvement. And the real breakthrough happened, in truth, last year. An American bunch of people called Leaf Labs in Cambridge, Mass, some MIT ex-graduates, produced a thing called Maple. And Maple looks like a tiny Arduino. And it uses this Cortex-M3. So they cracked the software problem. The only downside of Maple is it's inherited all of the difficulties of using electronics with it, and it's, by comparison, about twice the price. Whereas by comparison, you should be able to buy the parts one-off from RS and the board, and it would be cheaper than a mass-produced Arduino. So these are about 20 quid plus that. I believe that the parts for this are about 15 quid, including that-ish, if you go out and buy them. And so this is what you would normally see if you used an Arduino, and this is a classic Blink program. And the Arduino had the enormous insight that if you give people templates, kind of working little programs, where the syntax problems are basically solved, you can get started instantly. And it comes in the Arduino environment with about 80 to 100 example programs that all work. So it's very quick for children to start with something that works, and then you can ask them questions and they can fiddle around. And they kind of learn the syntax of C++ by osmosis. Whereas traditionally, we make undergraduates go through at least a month of pain before we actually get them to a point where they could make a Blink program, because we think we have to teach them about objects and classes and all of this sort of stuff. Whereas if you just start with a working program, you can actually get them to make something that works, get them to change a light into a buzzer and see if they can control the frequency. And at the end of these courses, which typically only last about 6 hours, I usually explain to them that they've just done a chunk of the first year of an undergraduate and they didn't whine once. So it's pretty good. It's a fork of the Arduino environment, so if you've seen an Arduino, this is green instead of blue. It's the ARM version of GCC under the covers, so you can do everything that GCC can do. And they've got two libraries. One is very Arduino-like, and the other is even lower level, because the electronics we've got is much smarter than an 18 mega. And they've got a USB bootloader, and that's important, because once you get it on there, you can plug a USB cable in and there's nothing else to do. It just works, as it were, and it blows. So, the reason that I popped along is if there are people, not now, but at some time in the next couple of years, who are interested in fiddling around and collaborating on this stuff, my goal, as I said, is just to get to a point where people from any age, 7 to 70, minimum bound, understand that they can make stuff. Because I think that's crucially important. There is evidence that there's a whole pile of learning that people do, which doesn't happen unless they physically do things. You can't sit and read something on a screen and type and get the same understanding as you can with a pair of wire cutters or a screwdriver making something. Our brains and our sensor systems appear to require quite a broad range of exercises, and only a subset of those exercises appear to happen when you type and look at the screen. I'm not saying that's sorted, I'm not even saying that's critical, I'm saying it's valuable. So there you go, folks, that was me.